Let's start recording. So hello once again, and today the topic of our webinar it's general purpose computing on GPU with OpenCL. And today, first of all, I'd like to make some introduction to general purpose computing on GPU. And next we will take a look on the architecture of CPU in comparison with GPU. What is the same, what is the difference in those architectures. Next we will learn a little bit about the OpenCL, what is it and how we can use it in our work to improve performance of some of our programs. Next we will implement two programs. First program, we will calculate the sum of two vectors. On the next one, we will convert the color picture to a grayscale. Next, we will discuss some moment connected to the performance and some other stuff connected to the GPU. So let's start from introduction. What is GPU and why we want to use it in our program and why we want to run some general purpose task on graphical processor. So yeah, as we have discussed, GPU first to letters is general purpose, and next GPU it's the name of graphical. It's just graphical processor. And usually a graphical processor is used for different graphical tasks, such different graphical calculation to improve performance of different games, etc. But why it might be useful for some general computation, like, I don't know, for example, matrix multiplication and some other tasks like filter different images, and why it is so popular to use a graphical processor in computation, for example, in machine learning tasks, and etc. So, and first of all, let's go back to the 2000 year, when each new model of CPU increases the frequency of processor in comparison with previous model. And Intel predict that they will achieve the 10 gigahertz chips by 2011 year. And now we know that it's not true. We didn't achieve such frequency. By this graphic on this slide, we can see that yeah, the increasing of frequency was good, but about 2004 or 2005 here, it's, I don't know if you can see my cursor, it's about here. This increasing frequency has stopped, and next it is almost the same value for all other processors. Sometimes it's a little bit less, sometimes a little bit more. And after those years, the central processors change their target from frequency to the increasing, for example, number of cores in the processor. And now in some modern computers, maybe in some server solution, you can meet the processor, for example, with 128 cores in one chip. But the frequency didn't increase for the last 10 years. And let's compare it with another with another graphic, and here you can see the comparison of CPU and GPU. Here we can see that the GPU continues to increase the powerful and outstrip the CPU in terms of performance. Here the performance is measured in terms of G flops. What is the flops? It's floating point operations per second. And so, for example, on this slide, G flops, it's
excuse
one.
me.
Yeah.
We have a black screen well, you share a black screen for some reason.
Did you see the slides previously?
Well, the first slide, we saw the first slide like on and off. It was, well, at first we see it, then it becomes black, then it returns to normal, then it becomes black, and we didn't see the second slide.
So sorry, I don't know why you didn't interrupt me.
So now it is black completely.
Okay, I'll try to reshare it. Can you see it now?
No, I still have a black screen.
Okay, I'll try to stop sharing. I'll try to give me 1 second. I'll try to reconnect to another Wi-Fi point. Maybe it's a little bit. It will be difficult to reduce the resolution. I will try it. Okay, sorry for this technical stuff. I'll try to reduce the resolution. Can you hear me?
Yes, we can hear you.
Okay. Let's try once again. Now it's really better. Can you see my screen now?
For now, yes.
Okay, please let me know if you want to see it or some other problems. So feel free to interrupt me and we will try to solve the problem. Did you see this slide and when I discussed about the CPU?
Could you repeat the question?
Yeah.
What did you? I mean, what did you say?
Yeah. Okay. Did you see this slide? This about general purpose computing with?
Yeah. I think everyone understood what this slide meant, but the next one we didn't see the next slide about yeah, this one.
Okay. So let's continue from this slide in this case. So on this slide, we compare the performance GPU in comparison with CPU, and here we measure the performance in flops. And yeah, as I have already told that floats is floating point operations per second. So gigaflops, it's 1 gigaflop, it's 1 billion floating point operations per second. And how we can see from this graph, the GPU has much more powerful in comparison with processor. In this case, why we need CPU? Maybe we can throw it away and work only with GPU. And let's compare the CPU versus GPU. Architecturally, the CPU is composed of just a few cores with lots of cache memory that can handle a few software threads at a time. In contrast, the GPU is composed of hundreds of cores and can handle thousands of threads simultaneously. Here on this slide, we can see some bullets about the CPU and GPU. So CPU has several cores, and maximum for the very powerful CPUs, it's about 128 cores for now, as far as I know. And for GPUs, it's thousands of cores. But the architecture of CPU allow us to work with low latency. Otherwise, the GPU allow us to work with high throughput, and CPU is good for serial processing tasks, and the GPU is good for parallel tasks. So thus, we can conclude that the task of massively parallel processing are good fitting to GPU architecture, and GPU can be very useful for boosting such tasks. So this is why it's might be reasonable to use the GPU for some general purpose task. Now let's take a look on the history of computation on graphic video card. So before the different languages for programming on GPU, the game developers it was necessary for game developers to implement some rendering of objects manually. They create the different algorithms such as detection of which stance we can show right now and on the next frame, and etc. Different algorithms of texture mapping and etc. And for increasing the rendering, some algorithms were implemented on the hardware level. And developers were able to use algorithms which were implemented on the hardware level by video card, but we were not able to send some their programs to implementing on the to execution on video card, and some not standard algorithms were executed on CPU. And for solving this problem, the hardware vendors who develop the graphical cards, they start to add some common algorithms to um, to the video cards which were implemented on the hardware level. But soon it starts to be clear that it will be impossible to add all necessary algorithms, and there is no reason to do it. And this is why they found the better solution is to give opportunity to developers to execute some their code on the processors of video card. And this is how the shaders were added to the OpenCL. It happens in 2001 year, and after that, we developed some languages like DirectX and OpenGL, and they start to be popular for game dev and some other stuff which connected with different video processing and some other stuff. And all those languages give opportunity to execute their developer shaders on the GPU and run rendering on any machine. And it wasn't necessary to developer to think on which hardware this software will be executed. Those languages take cares about it, and developers shouldn't care about it. And on the next stage um, of general purpose computing on GPU, it was the opportunity to run some other code, and now the programming for GPU is almost the same as for CPU, but there are some exceptions. For example, we cannot throw an exception from our general purpose program, which will be executed on GPU. Also, we are not able to use recursion. There is no function pointer and no virtual function, and some other exceptions. But all APIs which are used for general purpose computing on GPU, general purpose programming, they almost the same. Just I'd like to say that it's important to learn conceptions of GPU programming, and in this case, it will be easy to learn any new API like OpenCL, CUDA, Metal, and etc. So now let's speak about the architecture of CPU and GPU and take a look on the differences between them. As we have discussed, the main difference between CPU and GPU is latency and throughput. CPU has much less cores in comparison with GPU. Looking at the overall architecture of CPU and GPU, we can see a lot of similarities between the two. Both use memory constructs of cache layer, memory controllers, and global memory. A high-level overview of modern CPU architecture is on this slide. We can see that the modern CPU, it's all about low latency memory access by using significant cache memory layers. On this slide, we can see it. And modern CPU consists, of course, that contains separate data and instruction layer 1 caches. Yeah, it's here. Next, they supported by the layer 2 cache. And the layer 3 cache or last level cache is shared across multiple cores. If data is not residing in the cache layers, it will fetch the data from the global DDR4 memory. The cache sizes range up to 2 megabytes L2 caches per core for the modern CPUs. So, and now let's switch to the GPU. And if we inspect the high-level architecture overview of a GPU, it looks like the nature of a GPU. It's all about putting available cores to work, and it's less focused on a low latency cache memory access. A single GPU device consists multiple processor clusters. That contains a multiple streaming multiple processors. Each streaming multiple processors accommodates a layer 1 instruction cache layer with its associated cores. Typically, one streaming multiple processor used a dedicated layer 1 cache and shared layer 2 cache between pulling data from global graphical DDR5 or, for example, graphical DDR6 on newer GPU models. Its architecture is tolerant of memory latency. Compared to CPU, GPU works with fewer and relatively small memory cache layers. Reason being as that GPU has more transitions dedicated to the computation, meaning it cares less how long it takes the retrieve data from memory, but the potential memory access, its latency, it's masked as long as the GPU has enough computation at hand, keeping busy. So we can run a lot of tasks, and when some task waiting for some data from memory, another threads can execute some computations. So, and this is how the latency is hidden in the GPU. So, yeah, and on this slide, you can see the modern GPU. Those green rectangles, it's one core. So, modern GPU contains thousands of cores, and this allows us to execute a huge amount of tasks in parallel. Let's start to speak about the OpenCL. First of all, what is the OpenCL? OpenCL is an open source standard for heterogeneous compute acceleration. The OpenCL is developed by Kronos Group, and on this slide, I would like to show that the OpenCL can be executed on many different devices, such as CPU, GPU, FPGA, DSP, and a lot of other stuff. Only one thing which is necessary for you as for developer is that the vendor of this hardware should provide an OpenCL driver. In case if this driver is available, so you can run your OpenCL code on this hardware. And from this slide, you can see that a lot of companies are using OpenCL, and a lot of hardware vendors are involved to the development and improvement of OpenCL. So on the bottom of this slide, you can see some of them here. And on the top of this slide, you can see different applications which are using OpenCL for some accelerations. For example, a lot of programs for graphic processors, a lot of stuff from machine learning, and some other libraries. And before we will start to write some code, we should start from some definitions, which we will use during this presentation, and you will often meet them if you will develop in OpenCL. So first of all, our definition is host. Host, it is a program which executed on the CPU and responsible for configuring kernel's execution. Usually it is written on C++ language, and it responsible for configuring different buffers, different memory objects, different queues, and etc., and send some commands to the GPU, for example, or some another device where we would like to run our OpenCL code. So next definition is kernel. It's a function declared in OpenCL C program, and this program will be executed on a compute device. Before the kernel, before the function definition, which will be our kernel, we should use the keyword kernel qualifier, and kernels will be imputed on the compute device from command queue, and these commands we will send from our host program. And the last one, it's context. It's an object used by the OpenCL runtime for managing objects such queues, memory, program, kernel objects, and etc. All our common in the host program, we will configure our OpenCL pipeline in terms of the context. And on this slide, you can see the simple diagram. So on the CPU, we execute the host program. It sends some command to our OpenCL device, and the kernel is executed on this device. It reads the command from the host and execute them on this device. So all computations in OpenCL we run in terms of ND range. There n its dimension. For example, 1D range, it's the program which will be work with array of, for example, with arrays. 2D, it's with metrics or with image. 3D range, it's, for example, for some 3D data, like, I don't know, for example, image with information about the depth. I mean, not depth like RGB, but depth like physical depth. So on this slide, you can see the diagram of such 3D and D range. One moment. That maximum it can be 3D range. 4D range, as far as I know, is not supported by the OpenCL. And the execution of our kernels, we execute our kernels in the work items. Work item is independent from other work items, and it executes the code in parallel. And all work items, they join it to the work group, like here. It's the green group here. And also, we can tell that work group it's like the compute unit. Here, we will speak a little bit less about how it's mapped on the real device, but in terms of OpenCL, we have work item. It's one instance of our kernel which will be executed. Each instance, for example, we have, I don't know, 32 threads. They will be joined to the work group, and we have, for example, big task like 1,000 work items. They will be the whole task will include several work groups, and each of the work group will include the work item. And the OpenCL driver on the device is responsible for automatical start and work of the work items and the work group. For example, if we would like to run the million of processes, and we have only, for example, 100 of work items on our GPU, then the driver will automatically schedule each work item to execution. For example, one work item did all his work and finished it. Next, the OpenCL driver will submit a new work item to this core and execute it on it. And also, all work items in one work group has the same access to the local memory, and it's fast memory, and we can read to this memory, we can synchronize information, and sometimes it can be useful. A little bit later, it will be more clear. Now it's maybe a little bit difficult to understand. So now let's speak how it's mapped on the real device. So as we spoke, the work items are divided into work groups, which when work groups, it's just the specific of OpenCL. On the real device, we have some terminology like wavefront and warp. On the NVIDIA, it's a warp. On the AMD, it's wavefront. And usually the size of warp and wavefront, it's 32 on the NVIDIA and 64 thread on the AMD. And here we can see, for example, we have one work group, and this work group includes, for example, 128 work items in it. But we won't execute it all work items at the same time. First of all, it will be executed some part of them, which will be fit to the size of warp, and next another, and etc. etc. And um, this dividing on verbs, it's happened automatically, and we cannot specify any verb size on the OpenCL, and it depends on the architecture of your video card. And all work items in verb works synchronously, and they do at one moment one instruction. It will be the same instruction, and but with different data. And so it is necessary to understand that the instruction pointer for each work item in one verb, it will be the same, but the data in the registers will be different. And here we should discuss one question. What's happened if we will meet some code like here with if else branch, and for example in branch with true it will be 15 instructions, and in branch with else it will be 100 instructions. And let's imagine that um, for we are very lucky, and for example, our threads in verb predicate is true, and in this case, only 15 instructions will be executed. 10 instructions in else branch will be skipped. But in case when, for example, only one thread, this predicate for one thread was false, in this case, we have the problem, the name is divergence problem. And here on this slide, we can see the bad situation. For example, here one thread was false, has false for this predicate. And now we will execute the 15 instructions plus 100 instructions. First, when we will execute this code, those 7 threads will execute with 15 instructions. This thread will also execute the same instructions, but it won't save the results. And for else branch, also all those threads will execute those 100 instructions, but only one will save the results, another will do nothing. So, and in this case, for this case, it might be a problem. For some simple cases, this divergence problem is not a real issue, because it might not be affected on the performance. But in case when we have a lot of instructions in those branches, it can significantly affect on the performance of our program. So it's better to avoid such situation. So let's speak about the memory model of OpenCL. In OpenCL, we have 3 different types of memory. And first, it's private memory. It's very fast and very small, and it's available only for each work items, and we cannot get access to the private memory from one work item from another work item. Next type, it's local memory, and all work items in one work group has access to this local memory. This memory is also small and fast, but the advantage of this memory is that we can have access between the work items. And the global memory, to the global memory, we can put many different information. It's very big, but unfortunately, the access to this memory is slow. And global memory is visible for to all workgroups. And of course, we have a host memory. It's memory on the GPU. So when we create some buffer, some data, we should, for example, it will be like, I don't know, for example, pixels of our image. Next, we should translate this information to our device, to the global memory of the device. And all executions of in terms of OpenCL happened in terms of context. Here we can see some pipeline of execution OpenCL program. First of all, we have some OpenCL program. It's kernel here, and next we compile this program. And for example, here there is two kernels. It's .prot and above add. The next compiled program will also have those two compiled kernels. Next, we will create on the host side some memory object, like for example, input images or input buffers. Then we will, from the compiled program, we will create a kernel object, and we will map our memory object to the argument, to the input and output arguments of our kernel. And next, we will submit our kernel to the execution by using command Q. And all those steps will be happened in terms of OpenCL context. And now, to do it more clear, let's start to code with OpenCL. I don't know if you have any questions, we can discuss it now or maybe after the presentation. So feel free to interrupt me if you will have such.
I have one question. So we have this grid of cubes, like a couple of slides before. What does this actually mean? I mean, we have a separation into work groups, and the work groups have separation into work items. But why is why does this image have a 3D structure? Why not 2D?
So you asked me about the dimensions. Why?
Yeah, dimension. What are the dimensions here? Well, it says X, Y, and Z, but what do they mean?
It depends on your task. For example, you can use 3D image for, I don't know, for example, for the convolution, I don't know. Because in the machine learning, for the convolution, we will have, for example, 4 dimensions like batch, like channels, and like special dimensions like weight and height. So in this case, we can use 3D image to send such information. Like for example, in one dimension of this 3D image, we will send, for example, I don't know, batch multiplied on number of channels, and in another, it's for example.
Well, my question is, what was that image about? What does it represent? I mean, I know that there are work groups and work items, but where are they located? What is a work group? Well, where is it situated?
Do you mean how it's mapped?
How is it connected to the GPU?
Okay, yeah, well, good question. So let's maybe move to the picture with GPU. So here the architecture of the GPU, and when we will, for example, we have one task to the I don't know, compute the matrix multiplication, and for example, the output size of our task will be 100 on 100 elements. So in this case, we can use we will create the size of whole job. It will be 100 multiplied on 100, and we can create it's like 2D range task. Next, we can specify the division on the work groups. For example, we would like to split these tasks. I don't know. For example, one work group will contain 10, for example, work items. So it will be like we will have 10 work groups with 10 work items, and each work item will be mapped to one core of GPU, and the size of work group we can specify when we will compile our program. And it will be just like the number of in terms of GPU, the size of work group is how many cores, how many threads are in. So okay, work item it's one thread of GPU. Next, we will some numbers of work items. They grouped in the work group. So work group is just some number of threads which will execute our kernel. Is it clear?
Yes. And so, what is the next thing that was shown? So we have one small cube that is a work item, and there is the bigger cube that is a work group, and the whole thing is just like the whole structure of the GPU.
Sorry,
so yeah.
So could you please repeat your question just to be sure?
I mean, well, we have many work groups together.
Yeah.
So, well, why is it shown on the picture like that? Why are there so many work groups together? If they are, so we can process many kernels at the same time, and the number of work groups that are executed in the same time is the number of boxes here. Am I right, or is it?
Yes.
Why are there many? Yeah. Okay.
The reason of work groups is that the work group has shared local memory between the work items. So, for example, if we speak about this white cube and all work items in this cube, work items since it's one small white cube, we will have access to the local memory of this group. For example, we could read some data from global memory, save it to the local memory, and next use this information for each separate computation in separate work items. And if we would like to get access to the local memory of this white cube from another cube, it's impossible.
Okay. And so one work group is executed on one multiprocessor in the GPU. So what is the shared memory within the work group? what is the physical shared memory?
It's cache. It's L. So this is only one cache. Yeah.
Okay. And the memory of the work item is just a small portion that is allocated to one single core.
Yeah, it's just like registers.
Okay, and then why does the memory of the work group, why is the memory of the work group slower than the memory of the work item?
No, it's not.
It was,
yeah.
well,
Yeah,
you said
slower
that
because you how to say, just the your private memory is just the registers of thread. It's very close to it's very close to go to the registers to get some information from them and to take this data in your code. As you can see, the distance between the work items and L1 cache, it's also not so big. So this is why it's also fast, but it takes a bit more time. To be honest, it's usually it's using local memory won't really affect on the performance because we also have very fast access to the local memory. And I saw somewhere in the internet like the difference between access to the private memory and local memory, it's about, I don't know, 0.2 milliseconds or something like that. But I don't really remember. I think you can check it in the internet. But it's really a small difference between the access to those memories.
Thanks. That's my question.
So, okay. In this case, let's jump to the OpenCL. And first of all, which you should do to use the OpenCL, you should install the OpenCL drivers for your system. I didn't provide any instruction here because it depends on your operating system and on your hardware vendor. For example, on Windows, to install the OpenCL driver, I think it should be enough to install the NVIDIA driver for your video card. And in this case, you will have the OpenCL driver, and you will be able to execute the OpenCL program. I didn't check it because I don't use Windows, but you can do it. For example, on Linux, for example on the Ubuntu, it should be enough to install some packages from the repository with OpenCL drivers, and after that, it will be enough. What about macOS system? Unfortunately, the OpenCL is deprecated on the macOS. I think it should work. I didn't check it, but it should. And you can check that what OpenCL devices are available in your system by command CL info. I think the link to the CL info will be in the reference of this presentation, and you can find the source code on the GitHub. For example, on the Ubuntu, you can install it from the repository. For other system, you can maybe also you can find some installers or in the repositories, or you can just build it by yourself. And on this slide, you can see example of output. For example, for my Linux machine, I have two OpenCL OpenCL platforms. First, it's my CPU, and next it's my GPU with NVIDIA. So after when you install the drivers to your system, and you can see your device in the CL info, so we can start to write OpenCL kernel. As I have already told, the kernel program can be written in dialect of C, it's OpenCL C, or on C++. OpenCL C++, it's available in Kronos group, and you can try it. In this during this presentation, we will use OpenCL C. It's, I think, mostly common used language. And what won't work in the OpenCL kernel? As I have already told, recursion won't work. Function pointers, it's impossible to create dynamic arrays. In the OpenCL C, we don't have C standard libraries like std-lib and etc. But in OpenCL C++, as far as I remember, you can use some of the C++ standard library headers, but I'm not sure. It should be checked. And also, for example, you can use double, but maybe it won't be available for all devices. Usually, to use double, it's in the OpenCL, it's necessary to use some OpenCL extension. But OpenCL language has some specific. For example, it's vector data type. It's very nice type. For example, with float 4 or int 8, you can have 4 floats or 8 ints in one variable. And you can, for example, write float 4 multiplied float 4, and to get the result of multiplication, such structures, and you should write only one line of the code. Also, you have a half data type. It's like a float, but have only half of the size of the float. And also, there are many built-in functions are available, and you can take a look on the OpenCL quick reference card. It's just a lot of different functions which you can use during your OpenCL development. So in first our program, we will write program which will calculate a sum of two input arrays. Here you can see the code which we can use for the computation of sum on the CPU, and we can simply modify this code to the OpenCL kernel. First of all, I would like to notice that kernel always returns void. If we would like to get some results from the function, from the kernel, we should use arguments. And this function will be executed for each work item. So we can see that we don't have any loop in this kernel. We have some constructions like get global ID 0, and next we use this ID for calculating the values by some index. How it works? Usually when we execute the OpenCL program, we specify the size of our work, of our ND range. In this case, there is sum of computational of vector sum, so we can use 1D range, and get global ID returns the index of this work item in this range in our task scope. It means, for example, when we calculate the fifth element of our vector, get global ID will return to us 4, because we calculate indices from 0. So and we will calculate the fifth element in the vectors. So that's all what necessary to write for our program, which will calculate the sum of two vectors. So now we should write the host program. And there is some steps which we should do. First of all, let's prepare a program to work with OpenCL. Next, we should select OpenCL device on which we would like to execute our program. Next, we should compile our written OpenCL kernel, prepare everything for the execution, like different memory object, buffers, etc. Next, execute this kernel on the OpenCL device. Wait for when the work will be done. Next, read results. Also, we can measure execution time. Here we'll do it because it's interesting how we can improve the performance of our program. Next, we shouldn't forget to release allocated memory, and next we can try to run our program. Let's start to do that. First of all, it's necessary to include some headers with OpenCL library. When you will install driver on your systems, those headers should be available on your system. So it's the naming a little bit different for Apple devices and for all other. So we use ifdef here. And next also we include CI sort header. We will just use it for the errors handling. In the real project, it's better to write a better errors handling. We use assert only because it's fast, and in terms of our study project, it's useful. So next we should create three variables. First, it's device ID. It's identifier of our OpenCL device. To this device, we will submit our tasks. Next, it's CL context. In terms of this context, we will create different buffers. We will submit them, execute the kernels, and etc. And we should create the command queue. To this command queue, we will submit our commands to execution on our OpenCL device. And there is our function prepare OpenCL device. I just did it for more comfortable, so it looks in this way. We pass to these functions those three variables by reference. Next, we use CL get platform to get our available platforms. Here we take just first one platform. For example, for my computer, I think it will be Intel platform. If I would like to run on my computer on the NVIDIA, I should write this code in a little bit different way. I will show you a bit later how we can do it, and you will be able to see it in the GitHub in our project how it's better to do that, to select the device. And next, we can get an device. First, we try to get a GPU device on this platform, and if this platform doesn't contain any GPUs, so we will try to get the CPU. And next, we'll check the error code. Was it successful or not? In case if it wasn't successful, the program will be crashed, and we should investigate what's wrong here. So next, also in this program, we should create a context for this device, and we use for this CL create context. And next, we should create a command queue. Here we also use flag CL queue profiling enable. This flag is responsible for enabling profiling command, and we need this flag because we will measure the OpenCL kernel execution time by using OpenCL event. If you don't want to measure the execution time of your kernel, you can pass just null instead of this flag. After these steps, we prepared our OpenCL device, and now we can start to compile our OpenCL kernel. First of all, we use this simple function to read the kernel from file. It's just simple function which reads file to the string variable. Next, we compile the kernel. So we use our function to read the kernel. We pass the name of our kernel. Next, we modify string to the constant char array and use command cl create program with source. Here we pass our oops, sorry. Here we pass the variable with source code of our program, and this function returns to us CL program object. Next, we can build this program. Here we can use some our wrapper function. It will be on the next slide, and I will explain why we write some wrapper here. It's just will compile our program. And when the program was compiled, we can create kernel. Sorry, here it should be a new line here before CL kernel. I missed it while I prepared the presentation. So we use CL create kernel. We to this function we pass variable with our compiled OpenCL program, and we pass the name of the kernel. One OpenCL program can contain several kernels. So here we specify which kernel we would like to create here. And the next, we will use this object to execute this kernel on the GPU. So now switch back to the our wrapper function and why we did it. So this function takes the 4 arguments. First, it's our program which we would like to build. Next, it's a number of the devices and a pointer to the list of the devices. And the last one, it's options. So when we built our program by using function CL build program here, we can pass different options. For example, we can pass like options -g, and it will mean that some debug information will be collected during the OpenCL kernel compilation. And next, it can be used by some IDEs to debug the OpenCL kernel. Also, we can pass some options like for optimizations, like enable fast math, etc., etc. And why we implemented this wrapper function is because I would like to, for example, we wrote our kernel, but we did some mistake in the source code. And if you just run CL build program, it won't print any information about, for example, here you should, you missed comma or something like that. And in this wrapper function, I checked if the error code of CL build program wasn't successful. In this case, I used CL get program build info to get the information about the building procedure, and I just get some logs, and next I print them to the terminal. And in this case, for example, I missed the comma, or I don't know, I forgot to define the variable. I will see that in my terminal when I will call the CL build program. So next steps, on the previous step, we read our kernels and we compile it. Now we should prepare our memory for the execution. We should create, for example, here we will create the 3 arrays. It's first AR will contain the first vector, BR will contain the second vector, and CR it will be the vector with the results. We initialize those arrays, but all those arrays, it's just usual arrays. CL int is just, I think it should be just the same like just int. It's just OpenCL type. As far as I remember, it's just the same with C++ type int. So I can create array of integers here, or floating, sorry, or floating points. It doesn't matter. And on the next step, we should create the OpenCL objects, which we will pass to our OpenCL device, and OpenCL device will work with those objects. For task with calculating sum of two vectors, we can create buffers. So here we use function cl create buffer. First argument, we pass the context, in which context we will create those buffers. Next, we will pass some flags. First flag, it's CLMem read only. It means that it's constant memory. We can only read from this memory. And the second flag here, it means that when we will create this buffer, we should create, we should copy memory from host to the device, and this will be done automatically. If we won't pass this flag here, so next we should do manually copying by calling command its name clnq write buffer, and pass some arguments to this, and next copy memory from our pointer on the host to the CLMem object. Next argument is the size of the allocated buffer. The next one, it's pointer to the buffer with host memory, and the last one, it's argument to return the error if something went wrong. And B buffer created in the same way, and the output buffer we create with another flag. We use here write only flag. It means that we will write to this buffer only, and we pass null pointer. Not null pointer, just we pass null here instead of pointer to the host object, because we shouldn't initialize by any values this OpenCL memory object. And when we created those memory objects, we have on the previous step already compiled our kernel, and now we can set arguments for this kernel. For this purpose, we use function cl set kernel arg. We pass here the kernel object, next index of our argument, size of our memory object, and next pointer to this OpenCL memory object. It's simple here. And next, we can start to execute our kernel. I use here the std chrono to measure the execution time on the CPU. It means which time will be between the start execution on the GPU and when it will be end. The next argument is the size of our ND range. Here we create only 1D range. This is why this array contains only one element. And buff size, it's our variable which defines the size of our buffers. Next, we create CL event, and we will pass this event to the command which execute our OpenCL kernel. And by using this event, we will get the time which kernel used its GPU time. So which how many time the kernel was executed on the GPU. And to run the kernel, we use command, we use function clnq and drange kernel. Here we pass our command queue, which contains some our command, and our kernel object. This third argument, it specifies the number of dimensional in our ND range. So we create only one D range dimension. So it should be one here. It's offset, this null, it's offset in our task. So it's better to read in the documentation, but I'll try to quickly explain what is it. For example, we have some task. I don't know, for example, 1 million elements on 1 element, 1 million elements. So it's just huge size of work. And it is not possible to send all this job to the GPU per one time because we just won't have enough memory for this. So we can split our huge task on the some. It's not a. It's just on the some tiles. And next, create the different CLNQ and DRange kernel for each tile. And by this variable, we can pass the offset where this tile is located in terms of the global task. The next argument is global work size, which we specified here. And the next null, it's local work size. Local work size, it's the size of work groups. So we can specify it manually, or in case if a local work size is null, then OpenCL runtime is will create some local work size for us. So it's will split on the work groups automatically. Here, I don't care about how the device will split our task on the work groups, but sometimes it might be reasonable. For example, we would like to split our tasks to the work group, which will be good mapped to the size of our work of our GPU for better performance. And in this case, maybe we would like to specify the size of the local work group size manually. Calculate. We can get some information about OpenCL device and next understand which local work group size will be optimal for us. So we will specify it. Here I use null just for do it as simple as possible. Next, we use command CL wait for event just to wait when the execution time will the task will be executed on the GPU and to get some information to this event about profiling how the kernel was executed. And we use CL finish. It's just like barrier. We waiting when the all commands in the command queue will be finished. For example, we submit the kernel for the execution. We use CL finish to wait when this kernel execution will be done. And after that, I stop our CPU time. I get some time point for measure the difference between start time and end time. Next, when we executed our kernel, we waited when the kernel was executed on the GPU, we can read the results. For this task, we use CLNQ read buffer. So we pass our command queue where we executed our kernel. We pass pointer on. We pass our OpenCL memory object. These arguments we can pass here CL true or CL false, and it means, for example, when it's CL true, it's blockable operation. So we will wait until we will read the all elements from the OpenCL device. In case if it's CL false, we will just start reading and we can continue our program and return to the to this buffer a little bit later, for example. Next, it's size of the buffers and the pointer to the host memory where we would like to read the results. And here I print the 10 first elements of vectors. So I just save them to the string and print them on the screen. On the next step, we would like to measure the execution time. We can use for these purposes CL get event profiling info, and from our event we get information about the start time when we start profiling, when we executed our program, and read it through this variable. And next we can read the end time of our kernel execution. And next we can calculate the execution time of its GPU execution time, and we translate it from a nanosecond to a millisecond. And also we can we calculate the CPU execution time. And how it's better to measure the execution time. For this purpose, I create some structure which will return the CPU time and kernel time. And all our host program, I create a wrapper which names measure execution time. And each our host program, it's just like the function which returns this structure without any arguments. So we pass the function pointer to this measure execution time function, and next run it repeat times. For example, by default, it should be 10, I think. And next, calculate the sum of the times and divide it on the number of repeats. And next, next return the string with the average number of the execution time. So also we shouldn't forget to release allocated memory. We should allocate all. We should release all allocated OpenCL objects like events, memory objects like kernel, command queue, program, context, device ID. And next we can try to run it. So here is the screen how I run it on my Linux machine. I think in the end of the presentation I will show how we can run it on real machine. Just here's a screenshot. So we print the first 10 elements for each of our 10 runs, and we print the execution time for the CPU and execution time on the GPU. The next our task, I will try to go faster. It's only the source code, and I will stop only on some moments here. So on this program, we will convert color picture to the grayscale. First of all, we should write our kernel. Here, we will use textures. It's image 2D type. So when we use images, it's allow us also some benefits from using it. For example, here on the first line, you can see some variables like sampler t, and there is CLK normalized chords false. It means that the indices of pixels will be integers. Also we use CLK filter nearest. It means that when we, for example, would like to take some elements, for example, we ask to get the pixel 0.5 and 1. In this case, it will return the nearest pixel to this point. So it just helps us to interpolate some results. There is different types of the flags here, so you can read about them in the documentation. And we will use the very simple formula here to calculate the gray value. It's the summary of RGB and divided by 3. So first of all, we get position of our pixel. Here we use 2D range, and we would like to get the position position of our work item in the global task. So the ND range is equal to the size of our image. So the position in the of this work item in the global work size, it's just the same to the position of the pixels which we would like to calculate. So by get global ID 0, we get the first dimension. By get global ID 1, we get the second dimension, and we store it in the vector type integer 2, which contains 2 integers. Next, we use function read imagef, and we read from our image 4 floats here by this position. So next we get the pointer to this to start of this array with 2 floats, and next we just get the first element, second and third, and divide it by 3 and calculate the gray value. And next we save also this value to the float 4 and write to the output image here. It's simple. Here also the steps which we should do for writing our program. By bold, I highlighted the moments which will be different in comparison with previous our program. So first of all, let's start from compile OpenCL kernel, and here we only should change the kernel name. So here we just change the kernel name, and here to the name of our kernel in new file. On the next step, we should prepare everything for the execution. In this part, I use OpenCV for reading image, and I implemented this function. We read the image from file by using CV imread, and next convert color to the RGB BGRA format to have 4 channels in our image, and return it. And next we will work with this CVMat object. Next we should create the objects which will contain our memory objects for the images. First of all, we should specify the format of our CL image. We specify the channel data type. It contains integer 8 format, and this image, the order of channels is RGBA. Next, we create some description of our image. We define the type of our image, it's 2D image, and define the size of this image. Next, create image. It's almost the same like we create the buffers, just we pass the format and description. Here, instead of argument where we pass the size of the buffer type and size of the buffer. And in the same way, we create the output buffer. So next, we execute the kernel. Here we create the 2D range global work size, and first dimension in our ND range, it's the width, and the second it's height. And next we create we send our kernel to the execution, and only one difference is this number here. So we specify that now we execute 2D range task on our GPU. All other stuff is the same like for the previous program. And next we should read the results. We read results by function clnq read image, and we pass here the command queue, our memory with output image. We specify that it is blocking operation. Also, we should specify a region. It's the offset in pixels. From there, we should start our reading. Next, it's the region it's a rectangle which we should read from this memory. A row pitch, it's the length of each line in bytes, and slice pitch, it's the uh, size of slice for slice is 2D tile for reading 3D image. So in our case, for 2D image, it should be 0. And next, it's pointed to the array. So we created our array, which is the size of the image multiplied on 4 because we have 4 channels. And next, we create new CVMAT object from the pointer on from this memory and write it to the output image. Next, don't forget to release the allocated memory. And so here we execute our program on the CPU. The program, the project which I committed on the GitHub, you can specify the argument here like CPU or GPU to run your code on the GPU or on the CPU and to compare the results. So, and the results from the event and from the STD chrono, it's almost the same because they measure the same time of the CPU. And there is the input image for our program. And after execution of our program, we will have this output image. So a couple of words about performance. I measured the performance on Ubuntu 20 with the following hardware. I have Intel Core i7, sorry, and GPU is GeForce GTX 360. It's a very old GPU, and as we can see, our vector add for program with 1 million elements. Here the time for the CPU and time for the GPU, so it's about not 4 but 3 and something times faster on the GPU. And for the our program which convert color image to the grayscale, execution on the GPU much faster in comparison with CPU. So a couple of words about tools and debugging. It's almost all for today. So first of all, you cannot put breakpoint in the kernel code, but you can use printf and print some information to the terminal. I would say that it's a more useful thing. For example, you can write some if condition, like for example, if my global ID is equal to this value and to this value, so you will be able to print values for some specific work items. And next, to try to understand what's happened there. Another opportunity is to convert your OpenCL code to CUDA. It's very simple. The CUDA and OpenCL has very same APIs, so it's not very difficult to convert one code to another code. And in this case, you can use some tools from the NVIDIA, like NVIDIA Visual Profiler, NVIDIA CUDA memcheck, CUDA racecheck, etc. Also, you can try to use different profilers. For example, for Qualcomm, you can use Snapdragon profiler. And as far as I remember, VTune amplifier from Intel also has some OpenCL support, but I don't know what is the status for now of this OpenCL support in the VTune amplifier. And also, I worked with Snapdragon profiler, and I'm not able to say that it gives a lot of useful information for the developer. It's very strange program, to be honest. And another stuff, when I worked at Intel, they developed the Opencl Sdk. I don't know the current status of this project. It was very useful. With Opencl Sdk, you was able to get a lot of information about your Opencl kernel, how it was executed, and also one important thing, that you was able to debug your OpenCL code, for example, from Visual Studio, just to put the breakpoint, and you was able to specify that I would like to run this kernel for a work item with those coordinates, and next just go in the debugger like with usual program by your OpenCL kernel and to get some information about the variables and etc. So in the conclusion, there is some links to the repository, to the some code with some information about OpenCL, to the OpenCL quick reference card. And also I would recommend to read some optimizations and developer guides from the vendors of your target platform. For example, if you develop for the, I don't know, for example, for the Qualcomm devices and you would like to run your code on some Android devices, so you can download their developer guide for the OpenCL and maybe get some information, for example, some built-in functions which has hardware support and which should execute it in more efficient way on this hardware, for example. But for example, for Intel, they also has their own OpenCL optimization guide, so you can read some best practices how to write your OpenCL code more efficient. So today we discussed about OpenCL. We tried to write two different programs, and now let me show you how it will work. I will try to do that. It's really possible. So there is this repository on the GitHub I have created. So you can clone it and try to execute it on your own machine. Let me show you how it works. So let's clone this repository on my Linux machine. Give me a second. So let's clone this repository. Let's build it. So now we built this program. One directory was created here to make build release for my program. And here we have two executable files. So we can try to run, for example, our program which will convert our image from color image to the RGB. The file with image is already in the directory images. So we just read it and execute it. Wait for some time, and the execution time will be printed to the terminal. Now the execution time of the graphical device is a little bit bigger in comparison which was in the presentation, because now in parallel I have some tasks from my work executed on the PC, and they may utilize the GPU. For example, we can pass here the option with C. Let's do it for the vectors, because for the vector it's fast, it will be faster. So we can execute the vectors on the CPU, and the time is almost the same. We can run it from the GPU, and now you can see that the time of the OpenCL execution is much faster. So that's all for today. If just let me maybe. So in the repository, you can read some information, how you can build it, some description and some performance metric, how to run it, etc., etc. Also in the common directory, there is some common stuff such. Let me show. So you can read the implementation. So maybe it will be better. It will be faster just in the terminal. I don't know why, but the browser it's slow. So about the the folder with images contains this input image for our program, and color to gray output is just the image for the printing for the README file on the GitHub. So, and common function contains some, as I have already shown in the presentation, the this wrapper for the measure execution time. Also, all some other common function, also function for parsing command line arguments, and it's the function a little bit extended. So for the prepare OpenCL device, you can pass the last argument, which so the fourth arguments you can specify the device type here, and the last argument you can print some device information. So in the implementation, you can see how you can print different information about device. For example, you can get the size of available memory, etc., etc. A lot of different arguments. And here, as I have told, you can select the right platform. For example, here I get 2 platforms, and next I try to find a platform with GPU in case of GPU, or first platform with CPU. In case if I didn't find it, so I print the warning and I try to get the CPU device from the first platform in case if something wrong. So we will see the error message in the terminal. I think that's all. That's it for today. So if you have any questions, please. No, sorry, it's not all. There is the latest thing, I think, that I would like to say, that you can write your host program on many different languages, like on Python, Java, Go, Haskell, and of course C++. Usually, I think most of the developers write the host program also on the C or on the C++, but you can do it on the other languages, it's not a problem. But kernel code, you can write only on C or on C++ languages. So if you would like to write the, for example, OpenCL host on the Python, so just install some libraries for the Python and you will be able to do it. So thank you for your attention. I hope it was interesting to you, and please ask me any question if you have, we can discuss it. So I see something in the chat. Okay. So you're welcome. Hope it was interesting and it will be useful. You can use OpenCL in your, for example, research to speed up some of your tasks, some of your computation. So, and I'm glad if you will use it, and if it was interesting to you to see this presentation. In case if nobody has any questions, so
I have one last question.
yeah.
I mean, so if I want some algorithms from OpenCV to work on the GPU, Can I use OpenCL for that?
If you, sorry, I will repeat the question. Maybe I.
So I have so I want some algorithms from some computer vision algorithms to work on the GPU. Do I have to write my own implementation of the algorithm, or can I
It really depends. For example, if you write your own algorithms, and for example, this algorithm is not supported by, for example, OpenCL, it might be reasonable. It might be reasonable to write OpenCL implementation and execute it on the GPU. And if this task is good fit for massive parallelism, so in this case, it's you will get a good performance speed up.
Can OpenCV run on the GPU?
Yeah, this is what I would say on the next. In the OpenCL, we have in the OpenCV, we have many different backends which they can use for the execution of their algorithms. For example, you can compile it with Intel TBB and use Intel TBB for the speed up the execution. And also, as far as I remember, you can use the GPU. I'm not sure that all algorithms are supported to run on the GPU, but I know that OpenCV has some separate class. It's like GAPI, as far as I remember. I will write to the chat codes. It's GAPI. So you can Google about it, and this is a part of the OpenCV, and you can use some of the algorithms from this part of the OpenCV, and those algorithms will be executed on the GPU. But as far as I remember, in this case, you should use another class for the matrices and some other stuff. So the question, the answer to your question, that, for example, if you have already some library which has algorithms which you would like to use, first of all, try to run this algorithm by using this library. For example, maybe it will use only CPU, but the performance will be enough for you, and it won't be necessary to invest your time to the development some algorithms for the GPU, some code for the execution of this algorithm on the GPU. Also, read the documentation. Maybe this library can run this algorithm on the GPU. So in this case, you also shouldn't do this work. But in case if the execution time is too slow and you're not able to improve it by using this library, you can try to find another libraries, or you can try to write your implementation with OpenCL, and in this case it might help. Also, just it's not answer to your question, just I would like to mention that it is not, for example, sometimes I see the questions, for example, like what is better, CUDA or OpenCL? And I would like to say that the bad code written for CUDA will have bad performance, and also bad code which wrote on OpenCL will have bad performance. And I think that the same code written on the CUDA or on the OpenCL should have the same performance, because the technologies are very similar. Maybe CUDA has some NVIDIA extensions, but disadvantage of CUDA that you can use it only for the CUDA devices. So, and the same, for example, for the Metal. So this is why in the beginning of the presentation, and I told that it is necessary to learn concepts, not API, because the API is almost the same for many languages which created for the general purpose computing on the GPU. So did I answer on your question?
Yeah, thanks.
So do you have guys any more questions, or we will finish this? So let's finish. Thank you for your attention. Hope it's feel productive for you. And thank you. Goodbye.
Thanks. Bye.